Hello, my awesome chemists. We are going to start chapter 5 today, which deals with the modern atomic theory. And as always, in our study guide, we start with a little poem and then our learning targets. So this is a checklist that you want to check before a test or the exam. And this chapter is kind of an overview of what the modern atomic theory is, what we believe is inside of the atoms now. And of course, this is always evolving. And then we're going to focus on electrons because in chemistry, we care about chemical reactions, obviously, and chemical reactions happen by the transfer of electrons. So it is really important to focus on electrons, especially those valence electrons that cause reactions. So to start off, we're just going to review real quick the different models of the atom that we've studied so far. So we talked about J.J. Thomson's plum pudding model, where he said that the atom looks like a cookie, a chocolate chip cookie, where the dough is the protons, and then we have embedded in there the electrons. Then we went on to Rutherford's model. Remember, he did the gold foil experiment and found out that the atom is mostly empty space with a very, very, very tiny nucleus. Remember, we said if the nucleus was the size of a tennis ball, then the rest of the atom is a mile in diameter. Or if the nucleus is a quarter, then the rest of the atom is a football field. So very small, dense nucleus. At the time, they only had protons there. And then the rest of the atom is mostly empty space with the electrons kind of orbiting around. Then Niels Bohr came along, and by his time, we had found out that there are also neutrons in the nucleus. So the nucleus is very small and dense still. It has the protons and the neutrons now. And in the empty space around it are the electrons. But this time, Niels Bohr said that electrons are not just randomly there, they are in certain energy levels. And so the electron could be in the first or the second or the third energy level, not like anywhere in between. And he also came up with calculations for how to calculate how much energy an electron has at a certain energy level. He also came up with the maximum number that an energy level can hold in terms of electrons. So now, our current model is called the quantum mechanical model or the wave mechanical model. And we call it the wave mechanical model because now we think of these particles, especially electrons, having a dual nature. So they are matter, so they have mass and volume, but they also are like waves, which energy typically is what comes in waves. And so these electrons are thought to have a dual nature. They behave like waves, like energy, and they also behave like particles. So that's kind of mind-boggling. It's also known as the quantum mechanical model, and the reason why it's called the quantum mechanical, quantum means a certain amount. So each of these electrons can have only a certain set amount of energy. And this kind of actually kind of goes back to Bohr. Remember, Niels Bohr said that the electrons are in certain energy levels. So they could be in the first energy level or the second or the third or the fourth, but never in between. And that's the idea here, that the energy of an electron is quantized. It has a certain amount. It could be this amount or this amount or this amount. It can be anywhere in between. It can be a random number. One main difference between the wave mechanical model and Niels Bohr is the idea that the electrons, like I said, we behave like waves. The other main thing is that Niels Bohr thought that these electrons in these energy levels kind of orbit around in a certain path. In the wave mechanical model, we do not know what the exact path is or even what the exact location of the electron is. All we can do is calculate the probability of finding an electron somewhere in the atom. So, for example, if you can imagine an airplane fan, or just a regular fan even, if you think about it, so you know, if you have a fan around you, look at how many blades there are. Typically, most fans have 3 blades. We know that there are 3 blades there. But once you turn it on, the blades are moving too fast for you, for your eyes, to determine exactly where they are. All we see is a blur. From that blur, we can say there's a higher probability of finding it in one spot rather than another. But we can't really pinpoint. We're not fast enough to pinpoint and say it's right there. Because by the time we say it's right there, it would have moved. And electrons move randomly and very fast for us to be able to determine the path or the location. So all we do is we have these functions, these mathematical functions that we calculate the probability of finding the electrons somewhere. And we graph those. And then when we graph them, we kind of get a blob. So let me show you. So for example, let's go to this one here. So these are different shapes of these functions that we graph, these 3D functions. Imagine that these are 3D shapes. And so we take one of them, and then we take another one, superimpose it on it, and we take another one, and another, all these different functions for finding the probability of finding the electrons somewhere within the atom. So we put them all on top of each other, and we get a blob. We call this an electron cloud. And where you see this blob, you can see there are some areas that are pretty dark, right? Some spots here are pretty dark, and other areas are pretty light. Like there's a part right there that's pretty light. The darker that shading is, that means there's a bunch of functions on top of each other, so it gets darker and darker. That means that when you find a spot that's pretty dark, that means there's a high probability of finding an electron there. When you find a spot that is pretty light, like right there, that means there's a low probability of finding the electron there. So that's really all we can do, is graph these functions, and the functions are solving for the probability of finding the electron somewhere within the atom at some given time. And we get this electron cloud, or this blur, and we say the darker the shading, that means there's a higher probability, and the lighter the shading, the lower the probability. So we use shading to represent the probability of finding the electrons in a given spot in the atom. The denser the area, the higher the probability of finding the electrons there. The areas where there's dark shading, where there's a high probability of finding there, those are what the orbitals are. Orbitals are basically high probability areas where there's a high probability of finding the electron. By the way, if this does not make any sense to you, this whole lesson, it is okay. Quantum theory is very confusing. A lot of quantum physicists and chemists are, not really 100% clear about all this. So it is confusing. It's a very confusing topic, and it is okay if you're confused by the end of the lesson today. Next lesson should get a little bit clearer, and the following lesson should be even clearer. And so by the end of the second day here, or the second lesson here, if it's still very, very blurry and you don't really understand what's going on, then come see me. But by the end of today, it's not going to be super clear yet. So we talked about these energy levels, that electrons occupy energy levels. Well, what are energy levels? Energy levels are regions around the nucleus where an electron is likely to be found. And remember, we said that lowercase n is a symbol for energy level. So lowercase n denotes energy level. So we think of energy levels as like rungs of a ladder, right? If you have a ladder and you're climbing that ladder, your foot has to be on one of the rungs. It could be here, it could be here, it could be here, it could be here. You can't really have your feet just in between, right? You'd fall. It's just not possible. You have to put your foot on one of the rungs. And so that's the idea here. Electrons can be on one energy level or another. They can't kind of be in between. They have certain quantized energies. They're either at this energy level or this energy level. They have this amount of energy or this amount of energy, nothing in between. Now, when we think of rungs of a ladder, a regular ladder looks like this, right? So if you think of this as like your nucleus right here, maybe this would be your first energy level, n equals 1, n equals 2, n equals 3, and so on. In reality, it doesn't really look like this. It looks more like this. Now, that's a funny looking ladder, right? So imagine your nucleus right here. This is the first energy level. This is the second energy level, the third energy level, the fourth energy level, the fifth energy level. What do you notice? Well, it looks like they're getting closer and closer to each other, right? And that's exactly what happens in the atom. These energy levels get closer and closer in value to each other the farther you go away from the nucleus. Have you ever walked by and there was a fight and there were people forming a circle around, right? The first set of people are not really close to the fight. They kind of leave a little bit of space between them, but then as the circles grow and the layers of people grow, they get closer and closer together because they're trying to look in. It's kind of the same idea. You're trying to get to see what's going on in the fight, right? Well, these electrons are all attracted to the nucleus. And so the farther they are, the more they're like, oh, but I really want to be next to that nucleus. So they try to get closer and closer. And so they get closer and closer in value like this. I found this picture on the internet and something is wrong with it. I was looking up electron configurations and energy levels and stuff like that. And I found this. You see anything wrong with it? Well, it's kind of backwards. So according to this picture, this is the first energy level, second, third, fourth, fifth. That's opposite, right? So in reality, the nucleus would be here, not on the bottom. The energy would be increasing this way. This would be the first energy level, second, this one would be third, fourth, and fifth, because the farther you go away from the nucleus, the closer those energy levels become. Now, each energy level can hold up to a certain number of electrons. That number of electrons is 2n squared, where n is the energy level. So for example, the first energy level, you have 2 times 1 squared. 1 squared is 1 times 2 would be 2 electrons. The second energy level would be 8 electrons. The third energy level, 18 electrons. The fourth energy level, 32 electrons. The fifth energy level, 50 electrons, and so on. So on the test, I could ask you, hey, how many electrons are in the fourth energy level? Maximum. And so you plug it into the equation. Whatever the energy level is, that's your n there. So these electrons are on a certain energy level, on a certain rung of the ladder, right? They can't be in between. They are allowed to move from one to the other. Just like when you're climbing a ladder or going down a ladder, you can move your foot from one rung to the next, right? And so those electrons jump up and down these energy levels. A quantum of energy is the amount of energy required to move an electron from one energy level to the other. Okay, so electrons are really important in chemistry, as we mentioned, because chemical reactions happen by movement of electrons. So it is important to know a little bit more about these electrons. It's not enough to just know what energy level these electrons are in. We want to kind of get to know them a little bit more. And so just like, let's say somebody wants to find you, they want to get your address. It's not enough to tell them that you live in Ohio. Well, there's so many people that live in Ohio, they're not going to get to you. It's also not enough to just tell them you're in Worthington. Worthington has a lot of houses, right? It's not even enough to tell them what street you live on, because there's a lot of houses on a street. You gotta also give them the house number, right? And then when they have your complete address with the house number, they are likely to find you, right? However, they're not guaranteed to find you. Maybe you're not home that time, or maybe you're in a different room than the room that they go in. So it's kind of the same idea here. We can come up with an address for each electron. We can figure out what energy level it's in within so that corresponds to like the state, right? Within each energy level, there are sublevels that kind of represents the city, so we're narrowing it down a little bit. Within sublevels, there are orbitals, so that narrows it down a little bit to the street. And then within orbitals, there are electrons that have different spins, and so that narrows it down to the house number. But again, even if we know all this information about an electron, remember, we can't for sure tell its exact location or pathway. And so, like I said, they could go to your house and you're not there, or they could go to one room and you're in another room. So just because we can narrow it down, we have a high chance of finding it there, but not 100% sure that it's there. So let's talk more about these energy levels, sublevels, orbitals, and spins. So let's start with the energy level. That's kind of where the electrons are very broadly, kind of like, oh, what state do you live in? So we had already mentioned that energy levels are the level, or the symbol n, lowercase n represents the energy level, and we know that they go 1, 2, 3, 4, 5, 6, so they're whole numbers, and they start with 1. And we also know that the maximum number of electrons that can be occupied in an energy level is 2n squared. And then we also know, we've also talked about that the spacing between energy levels decreases the farther you are away from the nucleus. So let's look at magnesium. If you look at a periodic table, magnesium has 12 electrons total. If we wanted to know which energy level each of those electrons are, we would say, well, the first energy level holds up to 2 electrons. So there are 2 electrons somewhere in that first energy level. The second energy level holds up to 8 electrons. So there are 8 electrons in the second energy level somewhere. And then the third energy level holds up to 18 electrons, but we only need 2, right, to reach a total of 12 electrons. So these 12 electrons, 2 of them are in the first energy level, 8 of them are in the second, and 2 of them are in the third energy level. Fluorine has 9 electrons. 2 are in the first energy level. The second energy level holds up to 8, but we only need 7 more. Third energy level is empty. In fact, any atom has an unlimited number of energy levels. So there's an infinite number of energy levels in any atom. The ones that are occupied are usually a few. Like, we don't say that fluorine only has 2 energy levels. We say that it has 2 occupied energy levels. There's a third and a fourth and a fifth and a sixth and a seventh and a 100th energy level in fluorine. They're just not filled. So be careful when you're wording things. You say we have 2 occupied energy levels in fluorine, but an infinite number of energy levels in general in fluorine. Neon has 10 electrons. 2 of them would be in the first, and then 8 are in the second. And then again, we have the third one that's empty, fourth one that's empty, and so on. Okay, so that's the broadest thing that we could think of, is what state do you live in? Within energy levels, there are sublevels, and sublevels get the letter L as the symbol for them. And the number of sublevels correspond to the energy level. So the first sublevel the first energy level, n equals 1, has 1 sublevel. The second energy level has 2 sublevels. The third one has 3. The fourth one has 4. The fifth one has 5. The sixth energy level has 6 sublevels, and so on. The sublevels get letters. They don't get numbers. The first sublevel, which is lowest in energy, is called S. S is the lowest sublevel in energy. And remember, all these energy levels and sublevels and orbitals and all that stuff, these are mathematical equations of calculating the probability of finding the electrons somewhere. And so when you graph this function for the S sublevel, you get a graph that looks like a sphere. So let me go here. So here are the S functions, the S sublevels. They're spheres. So this is the 1s. That means the S sublevel in the first energy level. This is the 2s. The second energy level, the S sublevel. This is the 3s. Third energy level, S sublevel. This is the 4s. Fourth energy level, S sublevel. You'll notice that they all look like spheres. All the S's look like spheres. The difference is that the S in the first energy level is smaller in diameter than the second, than the third, than the fourth. Again, these are all equations, functions that we graph, and this is showing us the probability of finding electrons somewhere. So the S's look like spheres. Okay. Let's look at the next sublevel. The next sublevel that's a little bit higher in energy than S is called P. The P sublevel looks like dumbbells, and I think I have, oh, there we go. So there's the S, it looks like a sphere. There is the P, it looks like dumbbells. The next one is D, and it looks like a clover leaf, a 4-leaf clover. I think I have a picture. There we go. So there's the S is a sphere, the P's are dumbbells, the D's are 4-leaf clovers. And then we have the F, which is, they tell us it's a complex shape. I think it looks like flowers. I'll bring you a picture of it at some point. So we go S, P, D, F. Now these letters come from the names of different spectra. There's principal lines, diffraction lines, fundamental lines, and so on. So you don't need to know that, but that's just where those letters come from. Theoretically, just like energy levels, there's an infinite number of energy levels in any atom. Theoretically, there's an infinite number of sublevels in any atom. So they go S, P, D, F, and then they go through the alphabet. G, H, I, J, K, L, M, N, O, P, Q, R, S, and so on, except without the S. We skip the S, P, D, and F. So based on the elements we've discovered so far, we only need to use up to the F sublevel. Again, they go S, P, D, F. So the first energy level we said has only one sublevel, so it only has the S. Second energy level has 2 sublevels, so it has the S and the P. Third energy level has 3 sublevels, S, P, and D. Fourth energy level has 4 sublevels, S, P, D, and F. Fifth energy level theoretically has 5, S, P, D, F, and theoretically G. Sixth energy level would have 6, S, P, D, F, G, and H, and so on. Okay. Within sublevels, I know this is very confusing. We're going to put it all together at some point. So within sublevels, there are orbitals. Orbitals mean, like, if I graph the S function, I only get one graph. So I say I only have one orbital. When I graph the P function, I get 3 different graphs. And so I say I have 3 orbitals. The D gives me 5 graphs. The F gives me 7 graphs. So let's look back here. So the S, when I graph it, I only get 1 orbital, 1 graph. The P, when I graph it, I get 3 of them. 1 in the X plane, 1 in the Y plane, 1 in the Z plane. When I graph the D, I get 5 of them. 1 in the XY plane, the YZ plane, the XZ plane, and so on. When I graph the F's, I get 7 of them. So I say the S has 1 orbital, P has 3 orbitals, D has 5 orbitals, and F has 7 orbitals. So let's go back here. We said these are the S's, right? Let's look at the P's. The P's look like dumbbells. So when I graph the 2P, so the P sublevel and the second energy level, I get 3 graphs, 3 orbitals. 1 in the X plane, 1 in the Y plane, and 1 in the Z plane. So when you put them together, they look like this. Does that kind of look familiar to you? That's kind of how they draw sometimes the atoms. There's the 3P sublevel with 3 orbitals. The only difference between this one and this one is just the diameter, right? These are closer to the nucleus than those. The D's, when I graph the D, I get 5 of them. and then I can put them all on top of each other like this. Oops. There we go. And I get a blob, right? We keep getting these blobs. That's your electron cloud, right, from all these functions. Okay, so let's put all this together a little bit, maybe. So this table shows us how we came up with that 2n squared for how many electrons are in a given energy level. So let's look at this. Energy level is n, right? They go 1, 2, 3, 4, 5, 6, 7, and so on. The first energy level, n equals 1, has one sublevel. It just has the s. And the s has one orbital. Now, each of these orbitals takes up to 2 electrons maximum. And so since the first energy level only has the one orbital from the s, it can occupy up to 2 electrons. The second energy level has 2 sublevels. It has the s and it has the p. The s has one orbital. The p has 3 orbitals for a total of 4 orbitals. Each orbital takes 2 electrons, and so you get 8 total electrons. Let's look at the third energy level. The third energy level has 3 sublevels, s, p, and d. S has 1 orbital, p has 3, d has 5. If you add all those together, you get 9 orbitals. Each orbital takes 2 electrons, so 9 times 2 is 18. Let's look at the fourth energy level. The fourth energy level has 4 sublevels, s, p, d, and f. The s has 1 orbital, p has 3, d has 5, f has 7. So altogether, that's 16 orbitals. Each orbital takes 2 electrons, so we get 32 total electrons. Fifth energy level has 5 sublevels. It has s, p, d, f, theoretically also g. S has 1 orbital, p has 3, d has 5, f has 7. Guess how many g has? Yep, they go up by 2, so it has 9. For a total of 25 orbitals, so that's a total of 50 electrons, because each orbital takes 2 electrons. Sixth energy level has 6 sublevels, s, p, d, f, g, and h. Theoretically, s has 1, p has 3, d has 5, f has 7, and theoretically, g has 9, h has 11. That's a total of 36 orbitals. Each orbital takes 2 electrons for a maximum of 72 electrons. Now let's think about these s, p, d, and f's. Why is it that the s is the lowest in energy, followed by the p, followed by the d, followed by the f? Here's the reason. Remember, we said that the s has 1 orbital, so you can take up to 2 electrons. The p has 3 orbitals, so it takes up to 6 electrons total. The d has 5 different orbitals, and so each of these orbitals, remember, takes 2 electrons, so we can fit up to 10 electrons. The f has 7, and so you can take up to 14 electrons. Remember, electrons are all negatively charged, right? They repel each other. They can't stand each other. So imagine you go off to college and you are in a dorm that fits 2 people, and your roommate is your worst enemy. You cannot stand them. You fight, you fight, you fight. It takes energy to make you stay with them, right? Now, imagine that now you go to college and you are in a dorm that houses 6 people. And you are having to be a roommate with 5 people that you cannot stand. You are with 5 of your worst enemies. It's going to take a lot more energy to keep you in that dorm or in that apartment. Now imagine you are in an apartment with 10 people. So you and 9 more. And those 9 are your 9 worst enemies. It'll take you even more energy to stay in that apartment. Now, how about you with 13 of your worst enemies? So you can see the trend here. the more electrons we're forcing together because they're repelling each other, they don't want to be with each other, they need more energy to keep them in that position with a lot of other electrons that are repelling each other. So that's why the S is the lowest in energy, followed by the P, followed by the D, followed by the F. G would be even more energy, H would be even more energy, and so on. Okay, so last thing we're going to talk about here is something called the Afba diagram, or the orbital diagram. This diagram shows us the orbitals. So it shows us the energy levels, the sublevels, and the orbitals. And we can use it to kind of make a diagram for where all the electrons are in an atom. When it comes to electrons, we use arrows to represent electrons. So an up arrow or a down arrow, those represent electrons. Aufbau means build up. It's a German word, means build up. And we're building up energy. So it turns out electrons fill these energy levels and sublevels and orbitals based on energy. Nature likes low energy, right? So they fill from lowest energy to highest energy. So let's look at this diagram here. The numbers represent the energy levels. So this is the first energy level, second energy level, third energy level, fourth energy level, fifth energy level, sixth energy level. You can see that if this was my nucleus, this is increasing in energy here. Okay, the letters represent the sublevels. So the first energy level just has the S, right? And the little lines represent the orbitals. So S only has one orbital. The second energy level has the S and the P. S has one orbital, P has 3 orbitals. And you can see that the 2p is a little bit higher in energy than the 2s. The third energy level has the 3s, 3p, the 3d. And you can see S has 1 orbital, P has 3, D has 5. The 3s is lower in energy than the 3p, than the 3d. Next is the fourth energy level. We have 4s, 4p, 4d, 4f. 1 orbital, 3 orbitals, 5 orbitals, 7 orbitals. The fifth energy level has 5 sublevels, the S, the P, the D. And if we continue, there would be an F, 5F here, and then even a 5G here. Sixth energy level has 6, and so on. Again, you'll notice that the S's are lowest in energy than the P's, than the D's, than the F's. You'll also notice that the S has 1 orbital, all the P's have 3 orbitals, all the D's have 5 orbitals, the F's have 7 orbitals. So this is the order that the electrons fill up. So for example, let's say I have magnesium. Magnesium has 12 electrons. Okay, so the first 2 electrons go in the first energy level, and the 1s here. And we show that we have 2 electrons by putting 1 up arrow, 1 down arrow. That means they're spinning in opposite directions because remember they repel each other. Okay, the next 2 electrons fill up my 2s here. So I've drawn 4 electrons so far. Next in energy is the 2p. Notice it has 3 orbitals. That means it can take up to how many electrons? Remember, each of the lines takes 2. So it's a total of 6. So 1, 2, 3, 4, 5, 6. So far I've drawn 10 electrons. Magnesium has 12, right? So I need 2 more. So the next 2 go in the 3s. So basically what we've shown is a map of where each of these electrons, each of those 12 electrons are in a magnesium atom. It shows us each of the electrons, what energy level, what sublevel, what orbital they occupy. This right here on the bottom is the same exact thing, except it's in just one line. It might be just a little bit easier to draw. You can, if I ask you to draw an Afba diagram, you can draw it this way, or you can draw it this way. Either ways is totally fine. So let's say I have, I don't know, what element should we do? Let's do Let's look at the periodic table. Let's do scandium. So scandium has 21 electrons. Oh, that's a good one. So scandium with 21 electrons. All right, so the 1s takes up to 2 electrons. You put one up, one down. Then the 2s takes up to 2 electrons. 2p takes up to 6 electrons. How many have we drawn so far? 10, right? The 3s takes up to 2 electrons. So far we've drawn 12. The 3p takes 6 electrons. 1, 2, 3, 4, 5, 6. 18 so far. Next is the 4s. 1 and 2. So far we've drawn 20 electrons. One more because we need 21, so one more goes into the 3D. So again, this is a map that shows us what energy level, sublevel, orbital, and even spin each of these electrons occupy in the scandium atom. Tomorrow's lesson is called Electron Configurations. Hopefully it will clear a little bit of the confusion that we have from today's lesson. Have a great day, guys.